Welcome everyone. Thank you for joining us for today's expert webinar titled Data Engineering in the AI Era. I am Ria from SpringPeople, India's largest enterprise training provider, and I will be your moderator for today's session. In today's session, we have global certified AWS expert Mr. Rajeev Chandran, a distinguished technology luminary with nearly 2 decades of industry-leading experience, who embodies the essence of a visionary leader and architect of cutting-edge solutions. Mr. Rajeev Chandran has laser-focused expertise in data science engineering, ML and AI solution architecture, big data solution architecture, software engineering, and AWS solution architecture. Rajeev has left an indelible mark on the e-commerce, retail, search, and advertising sectors. In today's webinar, Mr. Rajeev Chandran will cover topics including distributed ETL, ELT, data engineering for generative AI, data engineering for traditional AI, data engineering for analytics, data lakes engineering, serverless in data engineering, data mesh. To all the participants, you can mention your questions in the chat box and they will be answered at the end of the session. Without further ado, let's start today's session. Now, I would like to invite Mr. Rajeev Chandran to start the session. Over to you, Rajeev.
Yeah, thank you, Ria. Good evening, all. Extending a warm welcome to this session on data engineering in the AI era. I hope to, through the session, I hope to, focus on the present day data architectures and stacks that are used for both in the traditional and in the non-traditional data space. While I also hope to bring to focus, if you are new to the data space, what kind of skills that you may want to add so that you could get into this new in this niche space, while if you're already practicing, how you could realign to get into the AI side of things if that has not been done. So let's get started. Okay, so what's data engineering? At the simplest level, it's just a set of operations to make your data available for your data scientists, analysts, and others within an organization. And these data is pulled from your operational data stores. So it's as simple as that. It's just about pulling up a data from a data source and transforming it, which becomes usable for and how you do it is what we're going to see in the coming set of slides. Okay, so before you understand data engineering, let's understand the broader landscape of this whole analytical world, starting with this this term called business intelligence and artificial intelligence, how they are. Okay, so your business intelligence is all about using statistics, inferential analytics, statistical analytics, inferential analytics, and predictive analytics to analyze a given data set. And with that, you kind of use with these set of analytics, you are able to get into this idea of how you could analyze a given data and make some meaning out of, make some meaningful decisions out of it, or get some inputs on which I could push my business further. So that's your business intelligence. Now coming to artificial intelligence, it's about doing cognitive analytics and generative analytics. Okay. Now cognitive analytics is all about doing analytics as much as humans would do, in terms of so you are given a data set and you want to get an output very similar to what a human would do out of their work, things like understanding a piece of text or understanding an image, etc. And in the generative side of it, it's all about how you become creative, how a machine becomes creative as much as humans would do. So on a broader context, you are solving, when I say what the data engineering does, it's preparing your data so that you are able to solve a business intelligence problem or an artificial intelligence problem through their respective analytics. Okay, so how does the data landscape look like? Okay, so when you look at the whole data landscape, it's made of multiple different stacks, silos, I should say, but well integrated, and there are multiple layers which you have to build on to enable a complete data analytics platform. So if you look at, so there is first of all, it has your data source. Now there are different kinds of data sources that are available. In today's world, data generation is so varied that you can't even imagine the number of sources that you may have. So you have your data sources, and then it's all about data engineering is all about collecting that data and then transforming it in such a way that it is consumable for those respective business intelligence or artificial intelligence analytics. So you have an ingestion layer, and which will do this processing. Then you'll have a layer where you have to store these data as this is come in, or either as it is processed. And then once this is stored, you want to organize it and probably even transform it for further reprocessing. Um, then further, once that's done, then you would start doing your analytics, and analytics could be anywhere between some search analytics to some queries that you may send across to understand that, and then you would also, as these analytics are done, you would also want to visualize it, create reports, etc. Now this is a platform that you will have to build up and for this you would need to have that data engineering role, which would actually help you to build it. So now the platform, that architecture that you have to build here could be for a batch processing, it could be for a stream processing, or it could be for an interactive session. Now this is not a homogeneous architecture. It will be a highly heterogeneous, catering to these three different ways of doing analytics, and each of these streams would further have a BI side of it as well as an AI side of it. So that's the other thing that you would need to take care. So putting all this together, you would need to build a platform which will handle the different types of processing for business intelligence and artificial intelligence. Okay, so let's look at some terminologies which are associated with in these analytical space, and how it all started. So there is this word called OLTP, and there's acronym called OLTP and OLAP. So OLTP is your operations data. And that's this is where the data gets generated. And once this data is generated and you want to utilize it for your analytics, that's where you call that OLAP. So so once you okay, let's yeah, so this is how it would look like. So it's your the transactional data. So the OLTP stands for online transactional processing, and your OLAP stands for online analytical processing. So your OLTPs are these original transaction databases, and then once this is generated, you want to use this for your analytical processing. So you would so through a process, of data engineering, you transform that into a analytical platform, which is what we call as OLAP. Now, earlier there was the source would have probably one kind of a database, but as of now there are different kinds of databases catering to different needs of the applications that may be so the earlier when we talk about the whole data analytics space, it was all about relational databases. Now today about there is this social media, and in social media maybe your data is not stored much in a relational database, but it may be stored more like in your a graph form. And you are aware of in the large internet organizations where there is if you look at an e-com site, there is where you would have you would have your own custom page which would talk about what products that you're choosing, whether you're saving that, and then later going back. So those kind of those kind of architectures need databases that are of different kind, which a relational database may not be able to fulfill. So now the choice of these databases are just going up in different ways. When we are talking of in the generative AI, the database itself becomes totally different. So this is how you want to look at how to understand where your data engineering would start with. Okay, so now let's look at the other aspect, SQL, NoSQL. So why is this there? So let's try to understand that. So SQL means it's relational. Okay, that's the expectation. It's relational and it's a single server architecture. So which is a single server architecture, that means the scaling is all going to be vertical. Okay, it's a vertical scaling single server architecture. That's the understanding when you talk about SQL. But when you talk about NoSQL, it invariably means that it is non-relational and it is a horizontally scaling architecture. Now, why are we talking about this? If you make a server horizontally scaling, by default it loses the relational properties. So that means you can't store your data much like that you would store in any of your traditional relational databases that you've been used to. Things like primary key, foreign key, various other constraints that you actually apply. So those are lost when you go in your non-relational architecture, and they would need to be rebuilt in different form. But out of the box, you lost this property. So that's the other important thing that you would need to understand when you are looking at what the whole landscape of data engineering is. Okay, now big data. So when we started off data analytics, it was all about a relational database, like a relational database like in SQL relational database, and maybe multiple of them are there. And then you were collecting data. You were collecting data through the data engineering process and pushing it into your OLAP databases. But they were all, they were not big data. When I say they are not big data, that means it did not have massive volumes. It did not have that velocity at which the data was being generated. It did not have a variety. They were largely structured data with a bit of unstructured or semi-structured data between. So you can kind of have an analogy saying that it was 80% really structured data and then around 20% non-relational or unstructured or semi-structured data. So it did not have variety. And then the data that were actually pulled out from your earlier data analytics from your traditional SQL servers, they were qualitatively and reliably, from a reliability perspective, it was very high, because they were transactional and there were enough checks put in such that the quality of data was really high. Contrary to today's world, when if it is in the big data space, we look at it such that there is a percentage of error that you're expecting uh, to be there when the data is of high volume and high velocity. And then from in your traditional data architectures, when I say relational data architectures, there was enough of meaning that were already available, while in the big data world, since the data sources are multiple and you would need to combine them to get more meaningful things. So it was more like a mining experience, where you have to go through tons of data before you could actually get some meaningful information out of it. So that changes the scope of the data analytical space from the original way it all started with. Okay, now types of data. So what are the kind of data that we are handling, whether be it your old traditional side of it or in the big data world? So basically, there are three types. There is the structured type, which are generally from the relational databases. There is semi-structured. Now, these are all those data which not only come from NoSQL databases, but also generated by various applications in terms of logs. And they could be in a form like CSV or a JSON or XML, etc. And then you have the unstructured. This is the space that we are today having a lot more analytics getting focused on. Okay, so unstructured data. So now that could be anything from a photograph to any sound based stuff, movies, etc. So these are the types of data, whether it's big data world or otherwise. These are all the types of data that are generated. And now, why we need to know these kind of data? Because the tools that you use need to be aligned such a way that you can process them. Okay, data transformation. Now, what is this about? Now, you have your data, your structured and semi-structured data, and this needs to go through an ETL process before it can be consumed, right? So what happens when you do an ETL for a structured or a semi-structured data? You generate a table. So a table is an organized collection of data on which you can then do various kind of analytics. What are the analytics that you can do? You can do a statistical, a descriptive, a statistical analytic, which is a descriptive based, inferential analytics, or a predictive analytics. And you get, when you are applying this, that means you applied a business intelligence and you expect some meaningful information out of this. So the ETL that you apply for different types of data structures are different, and the outcome or the output of that transformation also varies. So if it's structured, semi-structured, you are eventually having it in a table format. So what happens if it is an unstructured, and do you do an ETL? You do an ETL. And how do you do an ETL? So if you look at in the data transformation, I've used SQL in the ETL, but there may be other things that you may apply as well. Maybe a programming language can also be done, but largely today the focus is about using less of programming and use more of SQL. Now, when it comes to unstructured, the whole tool changes. We are talking of a set of tools that is totally different from SQL. They are frameworks which needs to be dealing with an unstructured data. As an example, if I take a photo, if I get like any image, and that image has a background. It could be any kind of background. Let's say, it could be a mountain or a sea, and then there are some people standing, or there's some vehicles. Now you should, when I do an ETL on an image like that, I should be able to extract those different pieces of different pieces of image, and then I should be able to make a sense out of this. That's the whole idea of it. So these set of tools will help you, scrape for information, and the output of that goes not as a table, it becomes a vector. And then therefore, it is through these vectors that I make up, that I get a sense of that particular data. So here, now our analytical becomes cognitive. That means it is making more human-like. Whether you, so when you hear something or when you look and see, you are able to identify what that could be, or you can make some sense out of it. So for that, you can't store it in a table, it becomes in a vector form. So that's why the data transformation and the ETLs that you apply on this varies based on the data structures. Okay, so how does the big data platform look like? So first, there's an ETL layer. And as you see now, there will be ETL layers. The ETL layers will change for the types of data structures that you're working on. And the ETL layer will have to work on streaming data, on batch, or maybe other forms of data that may be are coming in. So you would see that it is not just one type which you would have which previously it was working on. So it is of multiple data types, and more importantly, all the processing, the ETL as a processing, becomes distributed by nature. And then there is data processing. Now, once it is ETL and it is pushed into a data store, then you would have various kinds of analytics that you would apply on it. Now, the data may be, structured in answer, whatever that may be. So you could maybe doing a SQL, or you may be doing an AI ML batch. So you would have a layer for that. And we'll come into more detail understanding what those different kinds of layers are. And then finally, you will have a serving layer. So serving layer is that. So now this image is of that traditional big data platform. Now, how that changes a bit as we move into the analytical, we will see it in the next few slides. So this is largely the platform. Now, this platform, you can have it on-prem, or you could have it on cloud. And there are various ways of building it out. We'll see that. Okay, so data warehouse. So eventually it is about creating a data warehouse, whether it is business intelligence or an artificial intelligence. That is, whatever analytics you may be doing, it is all about doing this. But you do this differently for the different kinds of data structures that you have. So a data warehouse is an enterprise system used for analysis and reporting of structured and semi-structured data from multiple sources. So this is how it would look at. So largely, these would be from any systems which are relational or NoSQL by nature, and the format of the data that's coming in are either in a table kind of a structure, or rather it's a structured data, or it could be semi-structured data. You collect them, process an ETL, and then you put them into a data warehouse, and then based on needs, you would create your data mart. So this essentially is the a data house in the more in the present day time, while what we did not have in the earlier time was the semi-structured data, where there was no such a data source. Then okay, so what's a data lake? Now, this is a new way of organizing your data. When with the arrival of big data, which is largely in the late 90s, where you had organizations, I mean, rather to say these internet facing organizations, and when they generated data, we are talking of generating data of millions of users, contrary to a traditional enterprise, which would not be in that amount of millions. Like as an example, if you look at your traditional stores, even you take any of those big marts, which you may be going, so they would still have that. I mean, looking at scale, you can have it in few millions, but tens of millions was never going to be a choice for these kind of organizations. Yeah, that was scaled in the internet organizations, like your be it your Amazons and Facebooks and etc. So to handle such kind of data warehouses were limited, and they had to come out with something new. So a data lake is a centralized repository, much like your data warehouse, that allows you to store all your types of data, structured, semi-structured, and unstructured, at any scale. Okay, and you can store your data as is without having to worry about a structure in data, and then you can run different types of analytics on top of it. So from data warehouse, we are moving into an idea of data lake, which would now handle different types of. Earlier that I said, in a traditional organization, we are talking of before 2000s. It was all you take any organization, largely you would notice that the percentage of data that were collected, they were majorly structured and semi-structured. Or large, I would say it is 80% structured, semi-structured kind of nature, and then very limited unstructured data. Now, switch to 2024. Now we are talking of 90%, or even probably, okay, maybe you can say at 80%. 80% is unstructured and semi-structured data, and the percentage of structured data is kind of it just got reversed. The statistics just got reversed. So you would have to have a new way of organizing your data, and that became a data lake. Then what is a lake house? Now that you have your data stored in your data lakes, you had to do some kind of analytics there. Now that was becoming a bit difficult because there were challenges in the way you could organize it, much like in a data warehouse, and then consume it. When I say when you want, how do you want to do analytics? Again, it's those 5 analytics. Yeah, your descriptive, inferential, predictive, cognitive, and the generative AI, that kind of stuff. Now, so you had to find a way to organize this, and that became your lake house. So lake house is an open data management architecture that combines your flexibility, cost efficiency, scale of data lakes with a data management and transactions similar to your data warehouse. So that means your data lake, which now handled all kinds of the 3 different varieties of data, it can handle analytics as much as you could do it in your data warehouse. And you could do both your ML. Sorry, you could both do your BI and AI on this particular database stuff. So now you would reorganize it in such a way that you can now apply an ETL, while in the data lake kind of a store, we were rather copying more, and transformation was less. Now with an ETL applied, then you can transform it in a way where you could organize it in a table structure, or you could organize it in a structure much like your vector for your analytics of be it cognitive or your generative side of it. So now one storage, any analytics. Now that is what your the new way of looking at stuff is. So you have your data warehouse, you had your data warehouse, and then it would handle only your structured data. You had your data lake, which could handle any which would store any kind of data, and then when you marry these two, you get your lakehouse. And all of this was in today's world are organized into what is called as object storages. Earlier, the way of storing your data were in your classic your block storages, or file storage, and now that has changed to having it in your object storage, which is nothing but your S3 equivalent in other clouds. So you have now one storage, any analytics of those 5 kinds that I talked about. Okay, now that you've stored your data in a data lakehouse format, now the next step was to organize this data in a way that would be that would be accessible to different business units, or we would say that we are now making a data mart of these particular data. But remember, when I use the word, if I have used the word data mart previously, it is all about having data in a structured format. But here we are talking in terms of an unstructured format. So if you're organizing it in such a way, that has to be decentralized in its access. So if you're going to do it in a way of a data mart format, which becomes decentralized, we call it a data mesh. So organizations have multiple data sources from different lines of business that must be integrated for analytics. A data mesh architecture effectively unites your disparate data sources, links them together through centrally managed data sharing and governance guidelines. Okay, and yes, it could be this appears complex. Now having and implementing something like this needs a lot of management layers that you would need to build from a security perspective, and self-service. These are all going to be part of this particular architecture, and you're organizing into domains is another form, which is more like a data format. And another important piece of the data mesh is, now you saw up in the slides earlier that if I do an ETL on a structured and semi-structured data, that is more you are creating a table out of it. While if I use an unstructured data, I'm creating a vector out of it. Now can I then have a tool, or rather I should say, see now to do analytics on those tables, you have a set of tools, and to do analytics on this side of the thing, you have a different setup. Now can I have a single tool on which I would be able to query both the table and the vector, and then make a meaningful data out of that? Now that's that important piece the data mesh creates. And we'll look at all those kind of tools which we have. Okay, so the modern data platform looks a bit like this. So we earlier had a data warehouse, a data lake, which are more centralized, and now we are making it more decentralized. But remember, it is not just decentralization alone. We are creating now one lake. I mean, it's one store, any analytics, and it could be one tool doing all the analytics. So that means I am able to combine multiple different data types to give me more meaningful information. So that's the interesting part of it. Okay, so this is just a historical perspective of how it looked like in your. Um, uh, it started with your data warehouses, uh, lakes, and then what we have today is lake house. And when I also talk about lake house, it also means a mesh uh, for organized for one store, any analytic, and probably one tool. Okay, now how do you build it? How do you build these AI and BI tools, rather platforms at scale? And I kept using this word, one tool for all analytics in one storage. Now there are various set of tools that we have, and we look at them. So to build data platforms for big data, you will need to choose platforms that enable distributed computing, and that will be the first task. So distributed platform must support distributed SQL, which is not the property. This is not the property of a SQL server. Okay, it's a property of your NoSQL application. So it should be distributed SQL. We should be able to distributed machine learning. That's to do predictive analytics and otherwise. And we should also be able to deep learning, distributed deep learning. That is what is about your cognitive analytics and your generative analytics. And it all must be integrated in a single platform. Must serve both of these, all these three different types of analytics, while it should also do both. These it should do both your streaming and batch as well. So what kind of tools? So the first set of tool is largely for doing BI. I could also do some level of predictive analytics as well, predictive analytics, but that falls into the BI, the business intelligence side of it. This is distributed SQL. Like we talked about, there is no SQL, and I said the SQL properties are lost when you do a distributed SQL. So we have a distributed SQL, which are largely based on Postgres databases, designed pretty much like the NoSQL architecture. Hence, it supports your SQL data, distributed SQL processing. And remember, the relational properties are definitely lost. So a tool like this, you have your query engine and your storage engine, and we look at them both there. Next, you have your traditional Hadoop. So your Hadoop now, much like your distributed relational storages, it can have, but you store when you storing data in a distributed relational databases, they are in your structured format. But in Hadoop, we can store it in any format that you like, and still make a data warehouse of it as well. So this also has both query engine and the storage engine. Now, what's changing this scope is using a tool like Spark and a tool like Ray. Now, here the difference is these both are query engines. They don't have a inbuilt storage, or they don't come with a storage of its own. Now, what will be then the storage for these two kind of frameworks? Now, here the expectation is that I could use Spark on an Hadoop, or on a Postgres, or the most important thing, on my Lakehouse. Likewise, I can use my Ray, which can again go be used on your Postgres or on your Hadoop. and do the query where the data is actually kept. But remember, your array is focused towards machine learning and deep learning, while Spark can do SQL and machine learning and deep learning, while Hadoop is largely focused on SQL and ML, and your Postgres purely on SQL. So you should know when what tools to be used, and how do you want to build it up, and how the store and what kind of storages that you need to have. These set of frameworks, frameworks would help you, designing a distributed data platform, which is horizontally scaling. While of course you can do vertical scaling, but it is designed for your horizontal scaling. So as more and more need comes, you can just keep adding or appending resources that are needed. Okay, so the other side of it is just to understand a bit of, we are talking so much of distributed architecture, how the CPU, GPU, and TPUs change. Okay, so CPU, it's all about working with scalar data. There is, these today when we talk about AI in particular, we talk about these three kinds of data. There's a scalar data, there's a vector kind of a data, and then there is a tensor kind of a data. When you build your analytics architecture, you should have minimum of these to get that speed that you are looking at. So your CPU, you'd know, it's for where that you've been using otherwise, and with GPU, it's all about it's all about the SIMD architecture, single instruction and multiple data kind of architecture. So that's how it varies. So CPU can handle tens of operations per cycle, whereas GPU can handle tens of thousands of operations per cycle, and TPUs can handle thousands of operations, I should say, per cycle, because from a scalar you make a vector, from a vector you make a tensor, or you could say you make a matrix, and then from a matrix you make a tensor, but you don't have anything for your vector will also do your matrix processing. So you need to know what kind of thing. And the other very important piece in the distributed architecture, which you'd come across a lot, is about this idea of I think there's a typo there, data parallelism and model parallelism. We'll see what they are. Okay, so today, whenever you want to design a platform, and if it is distributed, then you will have to choose between what kind of parallelism that is needed. It's when we go distributed itself, the idea is to get much more much more speed there, or much lesser processing time for the amount of data that you would have, and of course there is the quantity as well. So this processing speed can be achieved if you take these two aspects called model parallelism and data parallelism. Now to look at data parallelism, it's just quite easy. Your data parallelism is nothing but taking a large set of data, splitting it, processing them on those individual shards, and then combining it. While model parallelism is slightly more trickier. It is like, example of, let's say you're taking a square root of a number. Now you can't have a parallel process of taking a square root of a number, because you need the output of probably the output to output of one to start on the next. So therefore, but having said that, there are other I just gave a very very unique case, but there are other processes, because eventually these are all mathematical processes that are happening. So there are definitely other mathematical processes that can go in parallel, and then we'll have to choose between these. So and you'll have to choose what frameworks to help this happening, whether it's in the data parallelism or in the idea of model parallelism. Okay, next, coming to serverless. Okay, so I'm sure you might be quite aware of a lot of serverless. We had started off with physical systems, then we moved towards your virtual machines, then you had your containers, and then finally you had your serverless. Right now, why are we even talking about serverless computing? It is all about building data, uh, distributed data platforms using serverless architecture. Okay, and how do you do that? And we'll see how they are actually. Okay, so we saw this, we saw the slide which talks about those different individual silos that needs to be built, right, for to enable your platform, the distributed platform that you are looking at. You had your ingestion layer, your data stores, your catalog and processing, search analytics, visualization. So these are the layers that you need to build into your data platform, and you have to build them um, in such a way that I can use a container as a service or as a function as a service for each of these individual tools. So if you have to build a distributed architecture, either through a Postgres, a Hadoop, or a Spark, or a Ray, can I have them as a container as a service, or can I have them as a function as a service? And by default, all these are distributed. They are distributed by nature. But would you want them to be running as in virtual machines, or you want to run them as in a containerized environment? Okay, so when we are using the word serverless data platform, every individual of these layers become serverless by way of containerization, or by way of adding in a more function oriented way. So that's your serverless platform, having them in this structure. So if you look at a serverless BI architecture, so you have your applications that you want to use. Now and you will then connect to a query engine. So the query engine in this case could be a Spark, it could be some API of a Hadoop, or it could be an SQL API of a Postgres, or it could be an API from your Ray, right? So that's your query layer. But where is the data stored? Your data would always be stored in any of these engines. It could be an object storage, it could be relational, NoSQL, or some Hadoop kind of architecture. And there's a way to organize that table asset. So this is how this whole serverless architecture works, where you won't have those complex VMs. It's all about containers, and you look at it now from a query engine perspective and a storage engine perspective, and largely expect the storage engines to be an object storage, and you build a data warehouse layer on top of that to enable it. And likewise, if it's your AI architecture, it's pretty much the same. You have again a query engine and your storage engine, just that you won't have it in a table format, but here you would have it in your vector format where the data is stored. But remember, we are still talking of a single data store for doing both AI or a BI, and all that we are using is for an end user. He is not worried about what is the query engine. He is only worried about his connector. So in the case earlier, in the earlier case, he may just say that I want a JDBC or a ODBC connector and connect to the query engine. In this case, I'm just using an IDE and connecting to to be train or infer my analytics. So it becomes global development, local development, but global compute. That's the architecture without worrying about the complexities of doing it. So you would have to now build a solution of this nature, which is containerized from an object and having it distributed. Okay, now finally, coming to how it would look from, let's say, on an AWS. Look at this different set of tools. You have to build whatever that I've discussed on the AI MBA. You have in the middle of it, there is your data lake, and if you're looking at how you would do your ETL, there's something called glue. The governance is handled by various set of tools, which comes from your cloud, your AWS stack. And then there is, of course, if you have data governance in terms of security, then you also have data monitoring, for which there is a separate layer. And then you can then connect to this either through these IDEs, or through various tools. It could be even an Excel sheet that you may have, and you can connect it and get it. But remember, looking at the different set of tools that are used to build this up. Likewise, you have a similar setup with your Azure. There are the same now the object storage changes to blob, and it also has similar set of tools to design your solution. Okay, now coming to how how you'd want to build up a data engineering role, and how it is different, right? This is a very niche area today, a niche skill to have, extremely well paid, because we are looking at building a platform that is catering to all these 5 analytics. So you of course have these 3 different, I mean, there are a few more of that, but there is this very specific role called data engineering role. And if you ask me how you would build up, I would say it is these kind of these set of skills that you may want to have. First and the foremost, you should know your SQL well, without which you can't even start about it. And then learn about your Hadoop fundamentals. You should know how to use your you should know how to build containerized solutions. You need to know how to build a solution on-prem or on cloud, and for which you need to have a good command over your programming. And in this case, largely at this point in time, is Python. Maybe Rust is coming up, but presently it's all Python. And then you need to know your frameworks effectively, how to build for if you want to do your data transformation, you should know what tools that you're using in the BI layer and in the AI layer. And then when you're querying, you should know what tools to use to help you gain that information that you are looking at. So these are the large set of tools that you would actually want to build up over a period of time to get into this particular role. And lastly, if you're looking at how this whole landscape is, so there is, yeah, if you split it out, there is batch processing in the BI layer, there's stream processing, there is batch processing in the AI layer, and there's stream processing in the AI. When I say stream processing, it's all about real-time or near real-time analytics and the set of tools that you would. So these are the different layers. You have your ETL layer, your transformation or your processing layer, your visualization layer, training and inferencing. This is largely, or inference is largely exclusive to your AI layer, while you do training, visualization and training, you do it across these. But remember, the set of tools that you use would change. So now here in this case, you see for batch, for visualization, you're largely using SQL. And if you have to do some kind of a visualization at your AI, and you can't use SQL there. you would have to use a different set of tools. While training, I mean, there's difference in the way that you would do batch processing. When I say batch, this is where you're building up your whole LLMs and things like that. So you need to have a different set of tools there. And yeah, and so is the other set of things that you can have here. And look at ETLs again. It's all distributed. Again, there are changes for in the AI and the BI. SQL is largely restricted towards this side of BI, and whereas the AI it's not. Okay, so with that, I conclude on this session of data engineering in the AI era. Before I take some questions, I'll ask Kaushik to come in to speak something on this in this particular slide. Kaushik, you there? Kaushik?
This session. Rajeev, am I audible?
Yeah, you are. You are. Is Kaushik there?
Oh, thank you. Yes, Kaushik is here. So I was saying, thank you, Rajeev, for your invaluable insights on technology. I'm sure it was a very informative session for all of you. If you are interested in learning more about data engineering, check out our super discounted virtual instructor LED trainings batches on our website springpeople.com. These VIP trainings are delivered online, allowing you to learn from the comfort of your home with flexible schedules. If you don't find suitable batches, we'd be happy to discuss and schedule batches for you. If you live on, for live online sessions, if you are not interested in online sessions, try out our affordable self-paced courses. For more information, write to us at training@springpeople.com or call on the All right, thank you everyone. We appreciate your participation. We will be sending out the webinar recording to all the participants soon. Kindly provide feedback before signing off, as it will help the quality of future events. Thanks again for joining us today. On behalf of Team Spring People, we hope to see you again at our next expert webinar. Thank you.